Good day everyone, my name is Fuad. Welcome to our YouTube video. So today we'll be talking about representing curves, right? So there are majorly three forms of representing curves. So we have the explicit, we have the implicit, and we have the parametric form. So these are the three forms of expressing a curve. So this is a case of, let's say, y equals to f of x. This is a case of, say, g of x equals to 0. And this is a case of where you say r of u equals to x of u I plus y of u j plus z of u k. So these are the three forms. So majorly we'll be focused on the third form because these two forms, they have certain limits and restrictions. In the sense that, let's look at this for example. If we have y in the form of y equals to f of x, so let's say equation of a straight line, which is y minus y1 equals to mx, where we say y minus y1 equals to y2 minus y1 over x2 minus x1 x. Now you notice that at some point where x2 and x1 are equal, or we have the same value of x for y, that is at some point where the curve is vertical, we realize that this becomes unsolvable because we have zero share, which means we can't use this explicit form to represent straight lines. So that's one of the limitations. So implicit form also has its own limitation. So but with parametric, it can represent majority, if not all forms of curves. So that will be our major focus. So representing curves using this. So the general form of expressing a curve in the parametric form again is r of u equals to x of ui plus y of uj plus z of uk. All right. So then we'll move on to differential properties of the curve. So being like this, it has some properties. Basically, we are trying to look for some formula to ease our task for us. So the first property we'll be looking at will be the length of arc. All right, so we have the length of an arc. So say we have this portion of the curve. Yes. So, so let's say this, we have a curve. This curve is r of u. That's the function of the curve, r of u. Then we say, let's say we have this point P and we have this point Q, and the distance between the 2 points being the chord, right, is theta u. And so that's the distance between them. That is, when you say parametric, that means it's like in form, like you're expressing the curve in form of a parameter. So this curve now, we have point P, we have point Q, and the distance between them is a form of the parameter. Just like when we say we have y and we have x. X is the independent, y depends on x. That is, whenever x changes, y also changes, right? So that's just the same situation we have here. This change here is a result of there is a change in u. So we are looking for the equivalent of it in r. That is, let's say x changes from 0, then x becomes 1. Then y at that x, we have to look for the y at this point. So that means y is changing because x changed, basically. So that's what we're trying to do here. That is delta r. Delta r being, because we know, okay, let me just give the value for this. So this is r of u. At least this point is point r of u. And this point, as you might have guessed, is r of u plus delta u. So that's just what I explained. The curve itself is dependent on the parameter. Alright, so now delta r, when I do this, this means the magnitude, that is the value, the evaluation, that is the size. Is it 5, is it 10, is it 20? So that's what delta means. is equal to, obviously, that's point P minus point Q. Point Q minus point P. Our point Q is, so we have R of U plus delta U minus R of U. So we have the magnitude here also because I try to get scalar quantities magnitude. So how do we evaluate this? Then we use Taylor series. So from Taylor series, our R of U plus delta U can be said to be what? R of U plus the R du delta U plus the 2R du squared delta U squared, and so on and so forth. So like I said, like we know these changes, let's assume it's a change, it's a small value. That is, P and Q are very close. I'm just trying to make them larger because of analysis sake. They are quite close, but not too close. So we can assume that delta U will be a very negligible quantity, and then by the time you multiply it with this value, it becomes very small. So we can neglect the higher orders and only focus on the first two terms. So we can just say, which implies that our R of U plus delta U becomes R of U plus the R du change in U. Right. So now let's bring it back to where we add it here. So that is delta R, the magnitude of change in delta R. Again, delta R is basically just the distance between this and this, because there's a change in U, delta U. That means there must be a change in R, which is what? Delta R, which is equivalent to the distance between this and this. I'm just reiterating. So equals to R of U plus U is now what? R of U plus the R du, change in U, minus R of U. This takes away this. So we have that delta R is equal to what? The R du delta U. So this is what we currently have. So let me just clean the board so that we can count. Okay. So we have this now. So let's say this. Let's represent this. Let's say delta S. Let the magnitude of delta R be represented by delta S. So you are saying that when you evaluate this, the answer you get, let's just represent it as what? Delta S. Then we have that delta S equals to the R du change in U. Then we can also look at something else. Before we go there's a fundamental difference between this and this, between delta and D. So they both mean change, but this and they both mean small changes, or not necessarily small changes. At least not this. But for this means a very infinitely small change, very tiny change. So let's assume a case where this point is moving, and it gets really close. Let's say this is now P, gets very close to Q. This delta can change to this D. Alright, which means everywhere we have delta here, we can basically change it to what? D, so that we can continue solving. So we have ds equals to the R du du. Then just to simplify things, we can let the R du to be the same thing as R of U. We are all familiar with this. So that this represents this, so that our ds becomes just simpler. That's the whole point of it, du. Then we can integrate both sides with respect to ds, here with respect to U. So that at the end of the day we get S equals to then we have U naught U, that is from the initial value of U this is r, to whatever final value of u that we have. Then these are the u here. So this is one of the properties of a curve. So this is the length of arc. This is length of arc property of a curve. So I just take an example on that. So let's write what we have. That's u naught, the initial value to the final value, the u. So this is the formula for length of arc. So let's consider an example. Okay, so let's look at this example. Find the length of a portion of an ellipse where x equals to a cos u, y equals to a sin u, and z equals to b of u, bu. So solution. Solution. Alright, so we've been given the x of u, the y of u, and z of u. Recall that the general form of the equation of a curve in the parametric form is given by x of u I plus y of u j plus z of u k. So we have a cos ui plus a sin ui plus buk. Okay, so we said find the length of a portion. So basically we are using this formula that we have here. So what are the components of this formula? We are looking for s, u naught. We assume u naught to be 0 and this should just remain u. We have that. The u is just the u. Then we have r. This represents the r du. Remember, so we are going to be differentiating each term of this our general form with respect to u. So we can say r dot the r du is equals to. Okay, so let's differentiate each term of this function of this equation with respect to u. So a cos ui will get minus a sin ui plus we get a cos uj, sorry. Then here we get plus bk. So that's what we have there. So we have our r dot. Then we can just slot everything to this formula so that our s will equal to u naught is 0. Then we have u here. Then we have the magnitude of. Okay, before slotting it in, we still need to evaluate the magnitude because that's what the formula contains, magnitude of r. So the magnitude of r, being in this form, being a vector, will be simply us taking the square root of this sum of the squares of each of the terms. So here we have minus a sin u all squared plus a cos u. We don't take the ijk component, we just take those. So we take the magnitude in that particular axis. This is one axis, another axis, another axis. So the magnitude in that axis, which is this, this, and this. So those are the only things we are considering. Then plus b all squared. So what we get is we have a squared negative squared, that's a squared sin squared u plus a squared cos squared u plus b squared. We have a lot of common terms here. So we have a squared here equals to a squared open bracket sin squared u plus a squared cos squared u, then plus b squared. Recall that sin square u plus cos squared u will give us what? 1. Such that we now have square root of what? A squared plus b squared. So that's the value of our magnitude of r dot. So we have this, we have all the necessary components to be slotted into the formula. So So let's do just that. So we have x equals to 0 to u. So then we put square root of a squared plus b squared du. So obviously this is a constant term in this case, so because it does not contain any u's, so we can see it as a constant and we can always bring it out. So which will give us square root of a squared plus b squared 0 to u of du. When we integrate the u with respect to u, we get square root of a squared plus b squared equals to u. But we have boundaries, so we have 0 to u. So we have that times u, we have 0 to u. That is square root of a squared plus b squared open bracket u minus 0. That is the upper limit when u is u and the lower limit when u is 0. So that gives us a squared plus b squared u. Alright, so the equation for the length of arc. So if you actually have concrete values, then we can put them here. But our final solution is u a squared plus b squared. Done. Okay, here, so there could be a further question that states, find the equation of the above curve as a function of the length of arc. So what we just basically do, this is our length of arc, this is our parameter. Now our general equation is r of u equals to x of u I plus y of u j plus z of u k. Alright, so our general equation is a function of what? U. Every term has u. So the question is saying, find the above find the equation of the above curve as a function of the length of arc. So the above curve is the curve where our x was I don't know, a cos u, our y was a sin u, and our z was b. I think that's bju. Yes. So this is the curve. So they're saying that find the equation of that curve as a function of the length. This is general formula. This is general formula. So if we slot this in, then we've gotten the general equation, but we've not gotten it. We've gotten it in form of u as a function of u, not as a function of the length of arc. So to get as a function of length of arc, we make use of formula in this our question here. So to make use of formula, simply divide both sides by this term. So we get u equals to s over square root of a squared plus b squared. So this is our u. So anywhere we see u, we replace it with this value. So our x becomes s of square root of a squared. No, sorry. So instead of having a cos u, we have a cos s over square root of a squared plus b squared. Our y becomes a sine s over square root of a squared plus b squared, and our z becomes bs over square root of a squared plus b squared. Then based on those values, we form our general equation like we've done before. So we have that our r of, in this case, will now be a function of x. Now the x of ui is now a cos s over square root of a squared plus b squared plus a sine u becomes s over this a squared plus b squared, then plus I j, then we have bs over square root of a squared plus b squared k. So this is the final answer to the second question that we asked. So then we'll continue by picking up the other differential properties of a curve, but this time we won't prove them, we just state the formula, after which we solve an holistic question containing all the formula or all the properties. So we are looking at the other differential properties of a curve. So let's look at a curve from this perspective, because essentially a circle is also a curve. So this is the normal. Then here we have at an angle of 90 to the curve. So we have our tangent. Then here we have our binomial. So there are about five more or six more properties of differential properties of the curve. So we'll just try to list them out. So we start with our tangent. So this is basically this over this. So this is CR. Alright. So we at this point we understand how to get our R. So once you just get the R, then you get the R, then you get the magnitude of R, then you place them above one another, and then that's sorted. Then the next is our our normal. Sorry, our binomial. So our binomial is similar to the first one, but this time around it's this. So when you see this, since we understand that this is not scalar quantity, it's rather a vector. So this means cross product, not just direct multiplication of each term. It's a cross product. So hopefully we'll see how that plays out in an example soon. Then we have our normal. So normal is basically the binomial times the tangent. Something else to take note when we have a cross product is that b times b cross product t is not same as t cross this, right? So you have to take care. So when we solve it, the one that comes first is the one that stays on top, because you evaluate this in a matrix. So the first item in the matrix is this, followed by this. But we'll see that as that plays out. Just side of note. All right. So what other property do we have? We have this. Then we have curvature. So we have a curvature K. So our curvature K is this by this over this raised by 3. So it's this. Then we have a radius of curvature. Radius of curvature. This is a sign. The symbol is like rho. So it's basically 1 over k. So you invert this. So that's how you get your radius of curvature. That's so that's the radius of curvature. Then the last property we have is torsion. So we have torsion. So the symbol is tau. That's the symbol of torsion, and then it's a very simple formula. So it's also a fraction, so but the magnitude is across the two fractions. So you evaluate the fraction. So this is the fraction. Okay. So you get your binomial. After getting your binomial, then you differentiate it once to get b dot. Then you also evaluate your r. You differentiate it once to get your r dot. Then you evaluate the magnitude of your r dot. Then you place them above one another this way. Then you now evaluate the magnitude of the entire expression. So these are the other 1, 2, 3, 4, 5, 6. So that's the other 6 differential properties. So we have at least for this scope we have 7 differential properties of curves. So we have the length of arc, we have tangent, we have binomial, we have normal, we have curvature, we have radius of curvature, and we have torsion. I wish I could just write this somewhere so that when we solve, we won't bring it from somewhere else. No. Consider a curve represented as r of t. This one is not r of u. So just like every other thing in maths, the variables change. So we have r of t. So we have a cos ti plus a sin tj plus btk. So that's the equation of this curve. So we are asked to evaluate the tangent, the binomial, the normal, the curvature, the radius of curvature, and the torsion. So pick it one after the other. So fundamentally, we understand that all these formula they need us to evaluate what our r. They need us to evaluate our r dot dot. They need it. So and then they also need us to evaluate this, and also need us to evaluate Alright, so I'm just trying to simplify things so that this we don't have to just start solving things um, in between the questions. So we just have the necessary things and we just plug them in. So these are the ones I can recall for now. So we just evaluate this, then start slotting them into the formula. So again, our our r of t is equals to, I don't have to write it, there's not enough space. So we have our r of t here. We know that r dot means we differentiate this once. Right, r dot dot means we differentiate it twice. Then this magnitude means we evaluate the magnitude. No brainer. So we have equals to a cos t becomes minus a sin ti plus a cos ti plus bk. So that's our r dot. Then let's just evaluate our r dot dot. So this is going to give us minus a cos ti minus a sin ti. So this gives us 0 because there's no other term of t here. So we have this. So let's evaluate the magnitudes. So we have this to give us square root of minus a sin t all squared plus a cos t all squared plus b squared. So we have square root of a squared sin squared t plus a squared cos squared t plus b squared. So as before, we factorize this because a squared is common. Then in the bracket we have sin squared t cos squared t, which evaluates to 1. So you can eventually just have a squared open bracket sin squared t plus cos squared t plus b squared, so that we have a squared plus b squared because this evaluates to 1. So that's a squared times 1. As this is what we have as our the magnitude of r. So these are r dot dot, and then let me just put it somewhere up here. Okay, so for now our magnitude of r is square root of a squared plus b squared. So let's evaluate the one for r dot dot. So for r dot dot, so we have minus a cos t minus a sin t. We do not have anyone for k. So this evaluates to, so we have a squared cos squared t plus a squared sin squared t to give us square root of what? A squared, because that we factorize, it's obvious. cos squared t plus sine squared t. This gives us what? 1. So we have, at the end of the day, we have square root of what? A squared, which gives us a. So on the side here, I might just try it. The magnitude of r is what? A squared plus b squared, and then the magnitude of r dot dot is a. So we have this. So now let's try to get the cross product, then the magnitude of the cross product, then we can just start slotting them into the formula. Alright, so let's start with we are evaluating this now, cross r dot dot. So we have our matrix in this manner. We have I, J, K. That's our first row. And the second row are the elements of R, not R dot dot, R dot. So R dot is what? Minus A sine T, right? Just spread it as much as possible. Minus A sine T. Then we have A cos T. Then our K, we have B here. Then we can have this now at minus A cos T minus A sine T. We do not have any value for here, so we have 0 here. So then we just take the determinant of this matrix. Essentially, we do something like this. So this is the first term. So we have I open bracket. So sort of cover this. We are left with just this. So and then we cover this. So I left with this 4. This. That's A cos T times 0 minus B times minus A sine T. So that's for I. That's it. Then we have plus, minus, plus. So we have minus J. So similar fashion, we cover this colon and we cover this row. So we are left with this. So that's minus A sine T times 0, right? This times this. Then we have this times this. Minus B times minus A cos T. Then we are left with the last. That's K. That's plus K. Plus K. So we cover this. So we are left with this. So that's minus A sine T times minus A sine T, right? This minus open bracket A cos T times minus A cos T. So we have for this. So let's evaluate them. Okay, so I think I just ran out of space. So I'll also just do this. Okay, right. So we have so we can say I open bracket A cos this is 0. Then we have minus here. So this gives us 0. We have negative sign here. This gives us minus AB sine T. So minus times minus here we have plus. That's AB sine T. Then for J we have minus J open bracket what? So this also gives us 0. There's a negative here, there's a negative here, it gives us positive. That's AB cos T. AB cos T. Then for K, unfortunately we don't have zeros. So this is negative, that's positive. Then this A, so that basically the same, that's A squared sine T. That's plus K open bracket A squared cos T. Sorry, A squared sine T minus this one negative here, another negative here. So that's positive. So that's plus a squared cos t, a squared cos t. So we have ab sine t I minus ab cos t j. Then, like we've been doing before, we factorize this adds up to 1. No, sine squared cos squared. Yeah. So as before, this sine, so at the end of the day we are left with plus a k here. So that's our, so this is our r cross rr. Now let's evaluate r cross rr, the magnitude. So that's simply ab sine squared t plus ab cos t, then plus a squared. Okay. Sorry. So there's no so ab sine t minus ab cos t. So there's a minus here. Minus ab cos t, then plus a squared. So I'll skip to the bottom here since we have our proof so far here. So let me just add the one we just found now. This r plus rr gives us what? ab sine t I minus ab cos t j plus ak. So we're trying to evaluate this. I'll just continue solving this down here so that we have square root of what? This is a square here. A squared b squared sine squared t plus a squared b squared cos squared t. This is a squared plus a squared. So one thing we have here, we have a squared b squared open bracket sine squared t plus cos squared t plus a squared. So at the end of the day, this evaluates to 1, so that we are left with a squared b squared plus a squared. We can also factorize a squared out. So we have a squared open bracket b squared plus 1. Now being a squared, we can have it as times square root of b squared plus 1. I think somewhere along the line we missed our step here. This ought to be a squared. Somewhere along the line we missed our step. This ought to be a squared, so that this gives us a raised to power 4. So that this gives a raised to power 4. Gives a raised to power 4. A raised to power 4. So we are left with a squared here. And that's square root of b squared, or as we like to write it, a squared plus b squared. So that here we have a root a squared plus b squared. So the magnitude of r plus r dot dot is given by a square root of a squared plus b squared. So that's all we need for now. So with this, our tangent is given by this over this, which is dot minus a sine ti plus a cos ti plus bk all over what, yeah, this, that's square root of a squared plus b squared. So that's our tangent. Then our binomial, which is given by this by cos this over square root of this, is given by as ab sine ti minus ab cos ti tj rather, always this ought to be a squared, then plus a squared k all over this, because this gives us a open bracket a squared plus b squared. So we have a in common here, which we might decide to eliminate it. So eliminating this gives us b sine ti minus b cos tj plus ak all over square root of a squared b squared. So we have our tangent and we have our binomial. So our normal, so the normal is given by b plus n. So we do a cross product of what? B, our binomial. This is our binomial. Cos t, sorry. Then where's our tangent? We do a cross product of this by this. Our normal is given by. So we don't consider this. These are like they are constant terms. So we only be bothered about this. So we can bring them out. But so we have 1 over 1 over square root of a squared plus b squared times square root of a squared plus b squared. Then do cross product of I, j, k. Now b comes first. So we have b sine t minus b cos t minus b cos t. We have a here. Then we come back for our tangent. That's minus a sine t, a cos t. Then we have b. So this gives us a squared plus b squared because they cancel out. So we have 1 over a squared plus b squared. So I'll save our time from evaluating this. We just get the final answer for that one. To save our time, so I won't evaluate this one after the other. You just at the end of the day get minus open bracket a squared plus b squared cos ti minus open bracket a squared plus b squared tj. So we have a squared plus b squared common to both sides. So we could have 1 over a squared plus b squared times, if we say a squared plus b squared, if we say a squared plus b squared, then we could have what to be left. We have minus cos ti, what to be left here minus sine tj. Then these two can cancel themselves out. So that our normal gives us that minus open bracket cos ti plus sine tj. So that's our normal. So we found the tangent, the binormal, and then the normal. So let's go for the other one. The other one that's supposed to look for is the radius of curvature. So the radius of curvature k is given by cross this over raised power 3. So we'll just write it out of a squared plus b squared raised power 3. So we know that square root is raised power 1 over 2. So what we can say is we can express this as a open bracket a squared plus b squared raised power 1 over 2 all over a squared plus b squared raised power, there's 3 here, then it's more like we are having a raised power 3 square root of a raised power 3. So that's square root becomes 1 over 2, then there's 3 there before, so that's 3 over 2. So we have 3 over 2 here. So our k, you can have that as a open bracket a squared plus b squared, then they are similar, so this can come up here. So that's 1 over 2 minus 3 over 2. So my k gives us, then you do this simple math that's here. That's a open bracket a squared plus b squared raised by minus 1. So a over a squared plus b squared. So that's our k. And our radius of curvature is 1 over k. So that's a squared plus b squared all over a. So that gives us our radius of curvature and our curvature. So we are left with the last one, which is our torsion. So this is torsion is given by this. So we don't have b dot. Do we? No, we don't. But our b is, let me just check. B is b sine ti minus b cos tj plus ak all over square root of a squared plus b squared. Then our b dot gives us, so obviously this is just like a constant term, so we only bother with one up here. So to differentiate this, we have b cos ti plus, because by the time you differentiate this, you get minus b sine tj, so that's 2 negatives, so that's plus b sine tj. Then this doesn't have any t term in it, so that's just it. Then all over square root of a squared plus b squared. So that's our b dot. So we have our b dot, then the module of our r dot, that should be a squared plus b squared. So and then recall that we are trying to evaluate this, what is inside. Once we get what is, we have this now, we have this. So we will evaluate this, then we now evaluate the entire magnitude. So that b dot is b cos ti plus b sine tj all over, let me just on the board, over a squared plus b squared. So we have b cos ti plus b sine tj all over square root of a squared plus b squared. Then our this is given by, so let's just say this is 1 over, because it's that's b dot times 1 over this. So these are b dot times 1 over square root of a squared plus b squared. So this is square root, this is square root, so they cancel out to give us b cos ti plus b sine tj all over a squared plus b squared. So that's giving us that, it's giving us what we have here. So this is b dot all over, so this is what we have here. Now to evaluate the magnitude, so we have this, obviously it stays outside, so we have 1 over a squared plus b squared times square root of b, so that's b cos theta all squared plus b sine t all squared, sorry, t not theta, all squared. So this gives us square root of b squared cos squared t plus b squared sine squared t. So as usual, we factorize. We know that this will give us square root of b squared open bracket cos squared t plus sine squared t. This evaluates to 1, so we are left with what? B squared, square root of b squared, which is b. Then we should not forget we have this, that's over a squared plus b squared. So our torsion is b over a squared plus b squared. I'm just write it up here. Our torsion is going to b over a squared plus b squared. So that's everything.